Good morning, everybody, and welcome to the last day of the HLF 2025. My name is Helge Holden, and I'm the chair of the Abel Prize committee, and I will be the chair for the morning session. So it gives me great pleasure to introduce the first speaker of the day, Avi Wigderson. He's a true computer scientist and a mathematician. He holds the position of Herbert Maas Professor at the School of Mathematics at the Institute for Advanced Study in Princeton. Most of us in the audience have received no prizes. The people with the lanyard have received at least one prize relevant for this event. But Avi Wigderson is a unique person who has received 3 awards relevant for the HLF. He received the 1994 Nevanlinna Prize, now called the Abacus Prize, from the International Mathematical Union. He received the 2021 Abel Prize together with Lasse Lovac from the Norwegian Academy. And in 2023, he received the ACM Turing Award. So he's a true perfect role model for the HLF. Please, Avi, the stage is yours.
So, as Helge said, I got the Turing Award a couple of years ago, and I went back. We are taught as undergrads about the work of Alan Turing, but I thought that I should do a more serious job on reading his papers, and it was an amazing experience for me, and I want to share with you some of this experience, finding out the wealth of ideas and the depth of ideas that he had and some of their impact on us. Turing had, as many of you know, a very short life. That's more or less his CV over there, the place to spend time in. I'll tell you more or less about one paper from each period. I want to stress that there is much, much more that I cannot do. I have only 40 minutes. I will not talk at all about his work on building computers, which he did quite a bit after the war, about how much he wrote about the art of computer programming, which he, of course, initiated, about subroutines, his work on building computers, his work on the practice of programming. He talked already very early about subroutines, about libraries of subroutines, about documentation of software. He works on many areas in math. Central limit theorem is one. He proves as an undergrad a very powerful, maybe the strongest version of this. And it was done 10 years ago. He didn't know about that. His paper on numerical analysis is sort of amazing. We take for granted. I had no idea it was his, that he defined the condition number. He gave an algorithm for LU decomposition, things that are absolutely standard. He started his work on building physical encryption devices, his obsession with chess programming of computers. He works on the Riemann hypothesis. He believed it was wrong, and he was generating zeros to find the counterexample. So some of the algorithms for generating zeros of the Riemann hypothesis are still, some of his ideas are still used in such programs. Anyway, I'm not going to talk about this. First paper I want to talk about is this paper, the most famous paper, I guess. He was as a student in Cambridge, and has this fancy title, computable numbers with an application to the Einstein-Groups problem. It's hard to believe that this is one math paper that's probably impacted the world more than any other paper written. It basically brought on the computer revolution. We are taught this, some elements of this paper. Still reading it carefully, you find much more. I'll tell you about, I'm sure you'll know some of this, but I'll just repeat some of the main ideas there. So the way it happened, he took this course as a student on fundamental of mathematics, in which he was told about Hilbert's dream. Hilbert believed that in mathematics, truth is exactly the same as provability. Anything true can be provable, and moreover, anything provable can be, the proof can be found by means of some mechanical procedure automatically. And this dream was completely shattered, as we know. In 1931, Gödel proved this famous incompleteness theorem, showing the first equation is wrong. And then Turing was interested in the second and shattered this as well. Maybe. Yeah, have to be close. Proving his undecidability theorem. So to do this, you obviously have to formalize what computation means. What is a mechanical procedure? What did Hilbert mean, or anybody mean, by mechanical procedure? So this very general notion, and obscure and abstract notion, needs to be defined. Of course, people worked on this. Gödel had his own definition of recursive function. Church had his lambda calculus. And then Turing came up with this very familiar to everybody Turing machine. And both of these people were blown away and immediately considered that this Turing is the right model or definition of what computation is. Church named it Turing machine. And it's so simple that it is hard and needs to argue that such simple device captures all of computation, which of course Turing does in his thesis in 3 different ways. He claims, this is a Turing thesis, that this simple device that's so easy to build capture any complex form of computation. He shows it in, I'll move here. First, he shows that it emulates human computers. You may not know this, but at the time, computer was a job description for people. It was people who were called computers. It shows that anything mathematicians want to compute, or lots of examples, he gives programs to compute them on his very simple device. And he shows that it's equivalent to the other models proposed for a definition of computation. It's the birth of theory, namely computer science is a mathematical science. There is a formal model here that we can prove theorems about. In particular, there is a well-defined notion of what is a unit of time and what is a unit of memory. And so soon after, computational complexity could be developed in which you can bound this, you can classify computational tasks according to the time or memory they take as a function of the data length. And today, of course, we have many such complexity classes, and we study them. What he used this mathematics to prove the first theorem, his first theorem, the undecidability theorem. There is no algorithm to decide what's called the halting problem, which in layman terms just simply means that there is no algorithm, no computer that can debug a program. Christos Papadimitriou puts it in a very nice way, saying that computer science was born aware of its limitations. Let's say, unlike physics, where they had to find out the uncertainty principle or the second law of thermodynamics. This had a huge impact not just on computer science being born, but on mathematics, because finally there is a formal way to capture which structures can be understood algorithmically and which cannot. And there's amazing lines of work trying to study various structures in math, and Turing was among the pioneers again, showing that the word problem in groups, semi-groups, cannot be solved at all. They are undecidable. These are all reductions to the halting problem. And Matiasevich's famous breakthrough resolving the Hilbert tensor problem on the Diophantine equations, whether a polynomial with integer coefficients has integer roots. These have no computational solution. On the other hand, other fundamental problems, people started developing decision procedures too, like Tarski for the theory of the reals, and the Haken for knot theory. And in both cases, the algorithms was pretty clear that to do algorithms, you need to invent more structure. You need to discover more structure about this, like quantifier eliminations or normal surfaces and so on. So algorithms became much more part of math, and this understanding is still going on. The way Turing proved the undecidability, proved the hardness of this halting problem, is by what we know fundamental to computer science in general, that Turing machines, we can have universal ones that can emulate other Turing machines. So program and data are really equivalent, and this he uses in his proof for this technique we call today simulation and diagonalization. This proof technique serves us still today as a very strong proof technique of computational hardness. And for example, the same paper I mentioned before used it to prove that more time can buy you more compute. You can compute more functions if you have more time. You can compute more functions if you have more space. These hierarchy theorems. And with much more work, you can also prove a linear time version of the P versus NP question using this technique and some combinatorics. So these are fundamental proof techniques that we use. And you might ask at this point, why don't we know that P is different than NP? And I'll come back to this. Turing, it's far from obvious because it's just one paragraph. He talks about, computers, Turing machines. He calls them automatic machines. These are normal deterministic programs. But he has a paragraph talking also about non-determinism. I believe we are taught in college that this was defined much later by Rabin and Scott. He has a paragraph talking about choice machines in which the machine can have a non-deterministic decision whether to go to one state or another. And not only does he define it, he tells you why he defines this. He says that this defines what happens in proof verification. Somebody is supplying the proof and the machine just verifies it. So he's talking about proofs and contrasts them with computation. In fact, undecidability really proves the distinction. It's very easy to prove that a machine halts, but it's impossible to give an algorithm for halting. I move to the next phase of his life. He's going on the advice of Max Newman, the same professor, to Princeton because, as he's told, this is a place where everybody, that's the hub of computability. There's Church, Alonzo Church there, and his students, Kleene and Rosser, when Neumann arrived to the institute, Gödel was at the Institute for Advanced Study, and he goes there, and that's where he writes his PhD thesis. He didn't talk much to these people, I must say. In general, he was unhappy. In Princeton, he got an offer from von Neumann to stay there as a postdoc, but he returned to Cambridge soon after, like less than 2 years. Anyway, I want to tell you just about one idea that he puts forth in this thesis. In the thesis, he's asking himself, is undecidability, the only thing there? I mean, is the halting problem, for example, is the hardest thing, or there are more harder computational tasks. So he wants to understand, suppose the machine could solve the halting problem. Can it then solve every problem or compute any function? And for this, he invents the notion of an oracle machine, a machine that can access something maybe uncomputable, maybe extremely hard. What can it then do? And the notion of an oracle, of course, referring to the oracle in Delphi, which had access to maybe to the gods, trying to study what machines with oracles can do. And it's an extremely powerful idea that from its thesis on is still used extremely well in, today in theory. At the time, it was used to define new computational classes like the arithmetic hierarchy, and then more with the complexity theory, the polynomial time hierarchy. It uses a framework to understand random functions in cryptography, and is used to argue security. And actually, this Oracle point of view is also a way to argue why Turing's technique of diagonalization is not strong enough to prove P versus NP, to separate P and NP. So it is a fundamental idea that persists. Okay, as you see, this talk will just jump from one story to another. This is all I want to say about his thesis. He returns back home in early 1939, and of course, soon after the World War III and World War II breaks, III is soon to come, breaks out, and he joins the famous Bletchley Park Hut 8, and is entrusted with breaking the naval Enigma code. So the Nazis used this Enigma encryption device, I'm sure you all heard of, which was extremely hard to crack. And among the various Enigma devices, the one that was used by the Navy was the hardest. And it was extremely essential to break this code, because this is what the U-boats in the Atlantic were using. And I'm not sure how much you know about this, but thousands of ships from America with supplies and ammunition and weapons were sent to Britain, and thousands of such ships were sunk by the U-boats. I mean, this was critical for the survival of Great Britain in World War II. And of course, as is well known, Turing and his team cracked the Enigma code. They cracked it already in the late 1941. But the Germans never found this out. They never believed that it was cracked. So it really saved Britain, and Churchill famously said that this work in Hut 8 by Turing and his team was the greatest single contribution to the victory in World War II. This is an amazing achievement, and you think about it. This is when we read about it, you read that basically this machine, the bomb that in the picture on the right, this device that runs through many, many keys, potential keys for Enigma, are what was used. But it was amazing to me to discover how much theory and how many theorems Turing proved during this period. He had the peace of mind to realize that to make it efficient and break the code, you need to do mathematics. And he went on to work in probability and statistics and information theory. I'll do it briefly, but amazing work preceding lots of things we think were invented later. Here are two papers, one of the weight of evidence and one of population frequency that I'll tell you about. But you see, these are not Turing's papers, these are Good's papers. Good was one of the people on his team, and later became, work on these areas and wrote papers. But in many of the papers, he tells you the main theorem of this paper actually was told to me by Turing. So Turing didn't write it, but Good wrote it, and he said credit goes to Alan Turing. Weight of evidence, again, there are two notions, basic notions in statistics information theory. Weight of evidence has to do with the following problem. You want to distinguish two hypotheses. There are two probability distributions. You get a sample for one. How much confidence did you gain in this sample? Of course, this is, they cracked one message, one secret message. how much should they bias their search of keys to make it more efficient? How much did they learn? And the suggestion is to use this parameter, this random variable, log P of x over log Q of x. I'm sure it's familiar to lots of you. And so it suggests to study its expectation, its moment, so on. Today, it's known as this fundamental information theoretic quantity as a KL divergence, and they knew a lot about it that was later discovered independently by others, and this was used in the bomb. The other one is, again, a very basic problem in statistics. It's just estimating population frequencies. I stress this is so different than everything he did before and also later. He was all over the place. Here, suppose you have some NIID samples from some distribution over some alphabet. Let's say, okay. You want to, suppose that some element appears k times. What probability do you assign to it? K times out of the n. And our answer will automatically be k over n. But that's not the situation here at all. I mean, you should imagine going in the forest and you see 2 lions and 1 zebra and maybe 1 giraffe. What's the probability of a lion? Certainly not a half. I mean, you just show these animals. There are many more animals. I mean, the situation they are at is that the alphabet, the type of number of species is far larger than the sample size. There are many animals you didn't see at all. So how should you assign frequency? And they developed this very famous formula. You don't have to read it. It's a formula, it's pretty complicated. How will you assign probabilities given that you haven't seen even all the species? It turns out that this formula, they didn't prove that, but later it was proved that this is the optimal, variant of it which they knew about, is an optimal estimate, even if you knew the distribution. I will not even explain why it is subtle, what I just said. They completely understood this very, very basic statistical problem. And they did it in order to use it in the search for keys and breaks the Enigma code. Okay, good. So I have 2 more papers left, 5 minutes each, more or less. Now I have more. We started late. The famous paper on intelligence, on machine learning, he moved after the war to London to build one computer and was frustrated there and moved to Manchester to Max Newman, the same old mentor of his. I should say he was appointed in this extremely fancy position, a reader in the theory of computation. So he was a professor of theory of computation. And he wrote this paper, he wrote several papers on computing machinery and intelligence. And we know things about this, but I'll tell you some maybe things you didn't think were in this paper. First of all, in this paper, he introduces probabilistic computation. He introduces many things that are not obvious because he's preparing arguments for various people who will oppose the idea that machines can think, which is his main argument. So people say machines are deterministic, they're automata that do always the same thing. No, they can toss coins. And he starts with probabilistic algorithms. Starting to think about probabilistic algorithms, he immediately follows into what we, as a big theory of today, he starts with their theory of pseudo-randomness about, whether you have really random coin flips or whether it's just you are using a digits of pi on your computation. He defines more or less formally in the same way in the seminal paper in the 80s, defining random functions. They quote him because his definition is basically theirs, and he talks about unpredictability of values of the function given, some previous other values of the function. So he studies this, tries to understand this concept in depth, and this is a great follow-up for this work in the theory of computation. Of course, he's talking about learning, and I'll just have a few quotes. And one is that, again, as an argument against opponents, says machines are, the fact that you program your machine doesn't mean it will do what you want, because machines experiencing, interacting with an environment can change itself, can rewrite its own code. So it can be a learning machine. Machines make errors. We complain about errors within LLMs. He said that if a machine is expected to be infallible, then it cannot be intelligent. And he says the same about humans. He says we don't worry so much about humans, or complain so much about humans making errors. That's part of intelligence. And he's talking about analogy of teaching machines with the way children learn. And I want to stress here that of course, user experience, interaction with the environment is one, but educating of machines is very important to him. We heard Les Valiant on Tuesday telling us about his theory of educability. And he mentioned in the book that Turing already thought about this, but very little in the whole AI literature was devoted to discussing the education of machine. I should maybe say a higher level point. This is after World War II. Computers are started to being built all over the world. And what are they used for? Mainly, as you can guess, military applications, aiming better missiles and so on. Some are used for businesses like IBM. Turing seems to be the only one that already captures, understands that what we have here is a potential learning device, something that can learn like humans and write extensively about it. Of course, the main issue in the title, is the machine intelligence, AI. It's wonderful to read Turing. He writes extremely clearly, beautifully. This beginning of the paper say, how should I talk about this question, can machines think? I can, define what a machine is, and I can define what thinking is, and then you start arguing with me about the definition. I could rather go another route and just test it, right? So there's a philosophical point. He says there's objective ontological definitions may not be testable or may not be universal, and certainly are not falsifiable. And he rejects this. And he suggests to define this notion using just a test, a behavioral, subjective definition, because this can be made precise, and as I'll argue soon, it can be even revolutionary. So we all know the imitation game. I just flashed a slide that you are familiar with of the imitation game. You put a referee in contact with either a human or a robot, and you want them to tell you whether they believe it's a robot or a machine, or rather put a confidence, some number between 0 and 1, maybe, whether they believe it's a human or a computer. And a computer passes this test if these two numbers are roughly the same. The human cannot distinguish another human from a robot. And if a robot passes all of these tests with any human referee, then we might call it intelligent, or we might call it able to talk to people. Of course, today, in our world, we know that this test was already passed. We have intelligent enough, in this sense, machines, LLMs. But I want to stress that the point here is that this paradigm is suggesting for making definition remain with us and is extremely useful to us. So there are lots of precise imitation games we use all the time. This paradigm in which two things are the same precisely if they cannot be told apart. They don't have to be the same. They just cannot be told apart by any reasonable test, where reasonable has to do with your setting. So this is a paradigm that enables definitions, notions that were extremely influential. There are many examples in cryptography, pseudo-randomness, privacy, also in mathematics, in combinatorics and analysis and so on. And I'll just give one example of this, but I just want to stress another high-level point, is that in math, in computer science, definitions are sometimes even more important than theorems and construction and so on. Often they follow. Once you found the right definition, then you can continue with your theory. I want to give you one such definition in the style of imitation game for cryptography. So the most basic notion in cryptography is encryption. And we mentioned there are many encryption devices and schemes. And the question is whether an encryption function is secure or not. Or in fact, how should you define secure encryption? And this was done precisely in Turing style by Goldwasser and Micali. This is a fundamental paper which puts cryptography on a mathematical foundations. They say that an encryption function is secure if these two words are identical to any efficient observer, any efficient algorithm. The two words are simply an encryption of one message and an encryption of a different message. If for every pair of messages nobody can distinguish between them, then this is secure. It's a very tall order. It's a very powerful definition of security. Of course, they go on to give encryption schemes which pass this kind of test. Okay, let me conclude with the last paper I want to talk about. And again, we switch topics to something extremely far away from everything we discussed now. He's still, in Manchester. That's just 2 years before he died, he writes this paper. And the title is The Chemical Basis of Morphogenesis. This is a paper in biology. It's, in fact, one of the most quoted papers, over 10,000 citations in biology. And I wonder how many people knew that he wrote this paper? Okay, good. So what is it about? What is morphogenesis? You look at this picture and you say, what's going on? Something doesn't fit. Why? Where do the stripes come from? After all, this zebra, like any mammal, started from a fertilized egg. It's completely homogeneous entity, symmetric. How does this asymmetry arise? The stripes, or forget the stripes, even the legs, the spine, a direction. Where does it come from if we start with something completely symmetric? I don't know about you, but if I'm faced with this kind of problem, I throw my arms and go to think of P versus NP. I'm sure I wouldn't know what to do. So what you want to understand is how can asymmetry arise from perfect symmetry? You want a mathematical, or Turing wants a mathematical explanation of this. And he goes on to give you one. So he gives this quote. Again, there are many quotes in this paper. It's really amazing. You see his ambition. In this section, a mathematical model of a growing embryo will be described. So he's going to tell you how an embryo evolves in the womb. Of course, he says, you can see a nice summary of the scientific method here. The model will be a simplification and idealization, and consequently a falsification, but it is hoped that the features we retain for discussion are those of the greatest importance for the present state of knowledge. It's just a summary of how we do science, beautifully written. Here's this model. It's a reaction diffusion model. That's how he calls it. And here's this model. This is the embryo. It's a ring of cells. So he has both discrete and continuous versions. And a state of the system is just the quantities of chemicals in every cell. So for every cell, you have a quantity of 2 or 3 chemicals, let's say. And the way it evolves is by reaction and diffusion. Reaction is within a cell, maybe some chemical reaction between the chemicals in each cell. And then between cells, quantities of the same chemical may want to balance themselves in some rate. Initially, we start with a completely symmetric and homogeneous situation. So all the quantities of each chemical in every cell are the same. And of course, if they are the same exactly, nothing will happen in reaction and diffusion. They will stay the same. I mean, they may change individually in every cell, but all cells will remain identical forever. And his point is that even though it's an equilibrium, it's an unstable equilibrium. If there's tiny, tiny difference between the quantities, then an evolution will take place. And under this evolution, you will get to other stable equilibria which have structure. And it goes on to prove it. And see how when this iterates over time, symmetry breaks and structure emerges, and he enumerates the structures that can emerge mathematically in various of these models. And you can have periodicity and clustering and stationary waves and moving waves, classifying them completely. And I should point out, this is maybe the first example of where computer science or computational, natural systems are viewed as computation, and at least he explains it. So here is some of the models that he discussed. He discussed two-dimensional ring. He discussed this as a sphere, and he discussed as a grid, and studied them all. He really invents cellular automata before von Neumann and Ulam. The two-dimensional model explains the whirling of leaves around the stem, the tentacles of Hydra. The three-dimensional model is really studying, he wants to understand the developing dimension of an embryo. I'm sure some of you know, maybe those with kids more, that in the first 2 weeks, fertilized egg just multiplies itself, and you get a homogeneous blob of cells that are all identical. And then around the 3rd week, a direction is formed. This is a form of the direction of the spine. This is called the gastrulation phase. And this is again explained by his model. He's studying more by simulation, not by analysis, this dappling of formations of color in on cows and zebras, etc. Anyway, I want to repeat what I said before, that this is the first instance where what we call today a computational lens on the sciences, that applying computational thinking and modeling to natural phenomena and theories of nature. And today, of course, there are interactions of this type between computer scientists and biology and economics and physics and math and social science that we see. And more, I would say this is one of the greatest import of the theory of computation into the natural sciences, and we'll see more and more computational modeling there. Okay, let me close up. It's a phenomenal experience. He writes so beautifully, so clearly. It's obvious, I mean, that he was a great thinker. He says, I was in one of these high school visits on Wednesday, and I always ask this question, and everybody knows who Einstein was, but maybe a third know who Turing was. And I think, it should be changed, basically. you saw the variety of things he's thinking about. At the same time, he was a scientist, he was a mathematician, he was a philosopher. I didn't tell you how much of an engineer he was. He really tried to completely understand. Once he wrote a paper, it's clear that he went through everything he could and developed, already complete theories. Of course, fearlessness is a clear feature of, being willing to go into all these areas. He understood the power of theory. I mentioned this especially in the World War II situation. Was extremely critical, and he was extremely critical of himself. I mentioned that in his paper on artificial intelligence, he creates already responses to various complaints of different natures about why, about machines cannot think. But he also evaluates his responses. And in one case, he would say, my response here kills the opponent. And in others, he says, my response is too weak. I should think more about giving a stronger answer. Brutally honest. If you read the papers, you see how clearly he thinks and how clearly he writes. And looking in particular for the simplest models that we see in these examples. And he didn't write many papers, but each one of these papers is just truly amazing. So this is it. Let me conclude with an advertisement for my book. If you want to read more about the theory of computation and its interaction with math, it's written for, you don't need much background to read it. It's written in high level, and it's also free on my website, so you don't have to buy it. Thank you very much.
Thank you very much, Avi, for a wonderful lecture. Even if we are running late, I think this talk deserves a couple of questions. So if there are questions from the audience, this one over there. Over there.
Okay, so I've had a theory for a hunch for a long time that the use of hidden Markov models in speech recognition came out of Turing's work in Bletchley and Enigma machine. Seems like finite state machine. And the hidden Markov model makes more sense for code breaking than it does for speech. I wondered if you had any. When I mention this to people in Britain, they wink, nodding. I get some body language, but nobody will confirm it. The Americans are a little better at sharing secrets, but I wonder if you have any thoughts.
I didn't see, concretely something that, looks like hidden Markov models in this, explicitly in his work. What I mentioned is this statistical or information theoretic, more higher level of looking at distributions, but I would assume there were, conditional in this study, and therefore you can think of them maybe as hidden Markov models, but I never saw that explicitly mentioned.
Okay, I think we take one question from a young researcher. There's a lady here. No, this direction.
Hi, so incredible presentation. So one of my questions is what do you think he would have done next? He was quite young when he passed away, and he's already keenly interested in everything, right? Really passionate. So what do you think he would have done next?
Yeah, it's very hard to tell, but his activity around that time was mainly in understanding of what can machines learn. He was, as I said, he was obsessed with chess programming. He understood that, maybe very early, that eventually it will beat us all. and was very interested in that. And so, and the other thing he invested a lot is in actually building of the computer and developing, I forgot the name of the Manchester computer. So in ways of programming it and getting more out of it, both in the hardware also, but also in the software. Yeah.
Thanks.
Okay,
Yeah, he could have gone to a completely different field. I wouldn't know.
let's thank Avi once more.